It's not sharing the slides?
Yeah, no, it should be. Do you see the, you don't see the, or,
I can see your cursor move. There you go.
so now you see the central control?
Yes, sir.
All right, cool. All right, so this one, if we've got everybody, this is just going to be a real quick high overview, and it's not even complete. I was up all night putting this stuff together. It's just going to be kind of a precursor and just an introduction to control system attributes and things. Next week will be far more detailed and focused with a complete slideshow. So I apologize for not having it done, but you know how the week's been. So anyway, I just wanted to go over a really high level flyby of control systems and the two types of control systems that that are out there. The first and most common type of control system is a central controller, where it's just like the CPC, where you've got one main controller, i.e. a control brain that is controlling everything. So you'll have circuit boards that are out there scattered around the system and around the site, but they're typically limited as a standalone. In other words, the boards can't do anything if the main controller is offline. They go dead if the control brain is not operating, and that's one inherent weak point, kind of an Achilles heel of a centralized control system, is that if you lose your main controller, you lose the entire process. So with that on a central controller, it's important to implement good fail-safe strategies and fail-safe measures in case you lose the controller, especially on mission critical items like on a grocery store or something, or if you've got critical cooling or something, that you want to make sure that there's a backup plan in the event that the system fails. So it's really important to be aware, it's important to be aware of how the system is going to operate or stay operating if the controller is offline. With a central control system, all the boards and everything that are out in the system, you have to address them and give them a specific location and an address, so that way the main computer board, the processor, knows where to send the signals and read from. So because the boards have to be addressed manually, there is room for some errors and things, and it occurs when the addressing goes wrong and gets wrong or gets changed and boards go offline, but it's pretty easy to correct. But it's definitely an attribute that you need to be aware of is board addressing. On a central controller, it's usually got a pretty robust and powerful processor, because it's actually calling the whole shots for everything, all the circuit boards, everything. Onboard memory usually is quite limited because it's not a computer system, it's a controller. So resources on memory are devoted mainly for the processor itself and for buffering and doing what it needs to do. Central controllers often don't have or don't contain an enormous amount of historical data. So they're reading the sensors and storing the values for a limited amount of time, usually a week or 2 weeks sometimes. The other advantage of a centrally controlled system is that a user interface is the human machine interface, HMI, is usually part of the controller itself. So you don't have to have a remote screen or keyboard or anything. It's usually part of the controller itself. So the central control can be kind of simple and have a small footprint. That gets us into, why is my keyboard not working? I guess I got to use my mouse. Okay, so a distributed control is a lot more powerful and capable. This is what Micro Thermo uses. So on a distributed controller where you've got all the circuit boards, each one of those circuit boards is its own specific controller. It's going to handle its own specific set of tasks. for whatever that board is doing, and it doesn't necessarily need any information from any of the other boards. And inevitably, we share a lot of information. So if there's an important bit of information that, let's say the rooftop unit board is controlling, but you also need some outdoor temperatures or outdoor humidities, or you've got a suction pressure control board and you want to know what the outdoor humidity is relative to the performance, there's a lot of information that can be passed back and forth from one board to another. Just, you know, the boards don't all have to have all the sensors on there. There's inevitably those sensors somewhere else, and you can just share that data. So because the downtime is so much less common, fail-safe is important, but it's not near as critical as it is on a central system, because the chances of you losing all of your boards all at once are pretty slim. It's pretty rare. Rather than having manual addressing to identify where the boards are at and where the computer has to send the signals, the boards all have an embedded identification from the control, or from the chip manufacturer. So you don't have anything that you can put the wrong address on and everything. It's all embedded in the board. Because it's a distributed control, the processors can be much smaller, since the focus and purpose of that little board is a lot smaller than trying to keep track of the entire site. And then that also has an advantage in that now if you have 50 boards and each one handles its specific processes, you can devote all the resources that processor is capable of to one specific task. So many boards, or create many brains, and it makes for a very powerful system. You can make some pretty amazing physics modeling and simulation type algorithms that really can react proactively rather than reactively. A drawback to a distributed control is that you need then some sort of interface in order to interact with the system and see what's happening. So with Micro Thermo, that interface is just a simple Windows PC. But since there's a PC there and you have the powerful resources that a PC offers, that allows you to do a lot more with the system, one of those being data storage. So where a typical E2 in a grocery store, or in a convenience store for that matter, will store a few weeks of data, a Micro Thermo system stores 5 years of data. So it takes every single temperature, every single switch status, every single command status, reads those values every 1 minute and stores it for 5 years. So, and it's a very valuable thing, having that historical information. We are going to be doing some training sessions on getting to that data and utilizing that historical data for diagnostic purposes and service purposes and performance purposes. There's an immensely valuable, it's a very valuable being able to have and get to that information and know what to do with it. So we're definitely going to be covering that as an attribute and advantage of the control system. So with that said, all the boards and the controllers have to talk to each other one way or another. And two of the biggest, most common ones, at least in our industry, by far the most common is the RS-45 transmission standard. Whether it's BACnet or Modbus, they all use a RS-45 standard to communicate. The other one that Micro Thermo uses is ECHELON, which is a protocol. That's actually a language and a communications protocol. But either way, both systems use a network of communication to talk to each other and to do what it is that they need to do. So with that, it's very important that that wiring, the controls communication wiring, gets done properly. This down below is just a signal example of what a 485 signal might look like, and it just shows that the DC voltage flips polarity from AC to DC for specific time segments, and this isn't necessarily what the signal looks like because it's not showing the amplitude of voltage when it's reversed. It's just showing you how you can flip these things, and the timing sequence, each one of these dotted lines basically represents a millisecond, I believe. So, you know, the first reversal for 1 millisecond would trigger a mark, which would be, you know, this might be 2 milliseconds, and then a space might be the immediate reversal of that for the same amount of time. And then another reversal at 1 millisecond. And then, anyway, it's not really illustrating necessarily a word or anything. It's just showing what's happening. And it's just changing the polarity on the wiring very, very quickly, millions of times a second. So here's an example of wiring practices. So for an RS-485, it's got to be, it's technically 3 conductors. It's a twisted pair, in that the twisted pair of the voltage is what's carrying the signals. But there is in there a third conductor, a ground wire, that grounds each board to each board. And the reason it's important to carry a ground from board to board to board is that if there's a voltage potential from one board to another, in other words, one board is subject to a base of like 0.2 of a volt for some reason, however it's installed, and there's a baseline voltage there. If a board's sending at 5 volts and the board's already measuring 0.2, you're not actually getting your true voltage signal that's attributed to the signal sent out by the other board. So having a connected ground like this from board to board to board along with your network cabling ensures that the standard voltages that you're getting are equalized from board to board. So that's why that's details shown there. So the other important attribute is then what you do with your shielding and your draining of the wire. So you're gonna, just like everything, just like all low voltage cabling, you're always gonna drain the shield down on one end only. You only ever drain the shield on one end of the cable. You never drain it on the other side. And the reason that is because you could have a voltage potential from where this wire starts to where this wire ends. And if you do that, it's going to carry that voltage down the wire and cause you even more headaches. The shield from segment to segment needs to be spliced and connected so the shield is non-stopping from the earth ground all the way to the end of the cable. And then at the end of the cable, it's got to be taped off and whatnot. So we will be doing some workshops and some examples of proper wiring practices one of these classes. And also actual site workshops where we're actually doing some hands-on training on these things. So the next slide is another attribute that you have to consider is the limitations of wiring. So this just shows the minimum and maximum allowable for segments. So a maximum overall of 1,200 meters. That's pretty far. That's about a mile. So it's pretty decent amount of networking you can do without running into not having a network too big. So you got to understand the limitations on distances on any control system. It doesn't matter if it's 485 or ECHELON. The other important attribute is terminations. So with RS-45, with E2 controllers or the RMCC, the older style controllers, you got to run a bus topology. So it's going to start at one board, move to the next, move from that board to the next, and from that board to the next, and so on and so forth until it gets all the way down to the end, and you're going to have a terminator over there. And the terminator is just simply a resistor. It's a resistor that establishes bus ohms on there for the communications to be able to send their signals cleanly. So if you have a base value of resistance on the network, your voltage signals are all basically standardized and travel at the same speed from one board to another board. So hopefully that makes sense. Does that make sense? So, all right, well, here's the last slide. Told you this was going to be close. This is an ECHELON LonTalk example of how you can wire ECHELON. It's a lot more free than just the bus. So up here we see a bus topology where you got a resistor at each end, just like we saw for the 485. Below that is a star, oh, excuse me, oh, good grief. Below that is a star configuration where the termination resistor is in the middle, and then it's just got 4 legs that go out to the various boards. There's a ring topology, which we never ever want to see because it's too hard to keep track of that. If you close the loop in the wrong spot, it can be a problem. So we don't usually want to see a ring. What we do at Costco, for example, and at Maverick, is we run what's called a free topology. So we just go from board to board to board, whatever is the easiest and the quickest. The termination resistor has to be kind of in the middle, so when you're measuring voltage way out here, or excuse me, when you're measuring your ohms way out at the ends, you want to be as evenly distributed at 52 ohms as you can. And again, I don't have any more slides on this because I ran out of time this morning. I've been up all night putting this one together. So we'll have more resources next one. This was kind of a inaugural thing. We had some hiccups this morning that we didn't have, so I blew through this 20 minutes faster than I did the one earlier. So anyway, you guys got any questions on this? Any particular facets of the control system that you want me to go over on the other classes? Earlier, some people asked about specific Micro Thermo training for Maverick. We are going to be doing that, but that'll be a kind of a branch by branch thing and a lot more personal with a smaller group. The other thing that we're going to get into is some of the more detailed CPC programming, flex combiners, and things like that. I need training on that as well. So we're going to be getting that set up. But other than that, for the general controller discussions, is there any specific things you think I should make sure that we hit on these future classes?
We have a chance to do this hands-on.
Yeah, there'll be labs.
Yeah, we'll do, like when it comes to the actual detailed training and specific training, that's kind of exclusive to core. Some of this stuff is, this can be, handed out to, this can go outside the company. But what I want to keep inside is the hands-on specific stuff where we're getting you guys to become elite skilled set of with an elite set of skills. So yeah, the hands-on training and stuff with actual workshops is going to be done, but not like in this venue. It'll be done like when I come up to the office, and we'll have boards and training boards and things and do some more in-depth details that can't be done generically over a big work session. It's, it's kind of a personal thing learning this stuff, and everybody learns at a different rate, so in a different way. So
Sounds good, Scott.
so yeah. Yeah, any other I guess that's it then for today.
Actually, can you hear me? Scott.
Yeah.
Now that we're getting Costco 644, and I guess that's a Danfoss store, is there any way maybe you can find any literature on Danfoss, maybe a couple slides just to refresh?
Yeah, I already, last night I already dug out I have a stack of memory cards here with like years and years of information on them, and I was digging out for my Danfoss stuff because it's like, doggone it, now I got to learn Danfoss. So, yeah, I mean, I don't even know how to log into that thing. We're going to have to ask Hussman, you know, they're going to have to hand us that information on how to log into the controller and everything because, yeah, I mean, for the past 10 years, I've done nothing but Micro Thermo. And then even before then, once I became a fan of Micro Thermo, I did everything in my power to stomp on CPC and Danfoss. So, but yeah, we will absolutely get some literature and training and resources on Danfoss.
Right on.
So,
Good.
All right, guys. Well, that was a short one, but that's good because, well, now I got to get Emily ready for school and take her to school and then head up to you guys.
See you in a bit.
You got any, who was on from Vegas?
I think they're gone already.
Oh, yeah, only 2 participants. All right.
Yeah, they're gone. I got just about everybody here.
Cool. All right. All righty, man.
All right, sounds good. Thanks, Scott.
Next week will be better, I promise.
All right, sounds good.
So, all right, man. See you later. Thanks.
All right, bye.